Good morning, everybody.
Morning.
So I'm going to spend a couple moments trying to explain DARPA, for those of you that don't already know this, because that helps a little bit for context. And then we'll talk a little bit about defense-related technologies and some of the things that we're working on, enabled, of course, by glass. So one of the things that was left out of my bio was the fact that I spent 5 years as a DARPA program manager. So when you're a DARPA office director or even a DARPA director, we're sort of giving back to the agency. The people who are having the most fun and actually doing the work are the program managers, and one of the things I got to do in that time period was look at gradient index optics lenses, which was probably the strongest connection I have to some of the topics that I'll be talking about today. But mostly I'm going to be bragging about what other people at the agency have been able to do. So if we go to the next slide, we'll start off with the fact that DARPA was, do I have the control? Sorry. Okay, I've got it now. So 1957, the then Soviet Union launched the Sputnik satellite, and it was a tremendous shock, I think, to the United States in particular, and to a lot of folks in the government. And the idea of being technologically surprised like that was somewhat disturbing, and a number of things happened, including the formation of the organization that ultimately became NASA. But a small organization called the Advanced Research Projects Agency, or ARPA, was signed into law by President Eisenhower at the time, whose mission was specifically to prevent and really to create technological surprise of our own. And that has evolved through the years, being called DARPA, and then ARPA, and then DARPA, and then ARPA. Currently, we're in a DARPA phase. I think we have been for quite a while. The Defense Advanced Research Projects Agency. And we're known for a number of sort of big deal sorts of things. Some of our greatest hits, I'll show you on this timeline. The top half is going to be military capabilities. These are the sort of the big system level things that you might read about a lot in the newspaper. And the bottom half are the enabling technologies, the things that a lot of our universities and small companies have made possible, and ultimately then led to a lot of dual use capabilities that have gone in many, many different directions. So on the top half, that is certainly things like stealth aircraft, miniaturized GPS receivers in the precision guidance and navigation category, uncooled infrared night vision, unmanned aerial vehicles, and on the bottom, lots of really interesting bits and pieces, starting off with kind of the creation of the discipline of material science. So pre-DARPA, you had metallurgists and chemists and mining engineers, people doing a lot of really interesting work, but the sort of the shoving together of the disciplines in order to really think about new materials, which ultimately led to a lot of very interesting alloys, composites, semiconductor materials, things like that, was something that DARPA actually pushed off very early in the 60s. And those original multidisciplinary centers can continue to this day under the NSF MRSAC program. So there's really interesting heritage there. You may have heard of a little experiment we put together called the ARPANET. And I'd like to point out that DARPA did not, in fact, invent the internet. We invented the ARPANET. Again, the National Science Foundation took that, turned it into the ResearchNet, and added university after university to create a really rich scientific network. And then, I hate to sort of destroy a good joke, but Al Gore and other policymakers were the ones who put into place the laws that turned it from a research network into the internet. Whether you love it or hate it, it is certainly not the thing that was initially envisioned, but it has done both good and maybe not so good in ways that it's clearly gone well beyond the ideas of any of the people who originally worked on it. So we take credit for the original technological breakthroughs, maybe not so much for the sociological phenomenon that it's become. A lot of work in AI, microelectronics, including a lot of the early breakthroughs in MEMS technologies. We conducted a really interesting set of races, of challenges on self-driving cars. Again, whether you like it or not, we are directly responsible for the creation of Siri. We had a program called Personal Assistant That Learns. Maybe it doesn't learn quite well enough, but that became Siri. And then most recently, we're very proud of some investments we made about a decade ago in a little company called Moderna, working on mRNA vaccines at a time that we were thinking it was mostly just good to help military personnel traveling around the world facing really interesting and complicated and maybe not so interesting diseases for which vaccines didn't necessarily exist. But in the back of the program manager's mind who started that was the idea that it might come in handy should there ever be a pandemic. So these are the kinds of things that DARPA has done throughout the years. What I want to do, of course, is pivot and talk a little bit more about glass. So let's talk not about DARPA, but let's just talk about glass in the use of defense applications. So over on the left, you'll see I've got a question mark after this. As you might imagine, as you go far enough back into the 1500s, there isn't a ton of empirical evidence. You can use, look at very old artifacts. You can look at patent documents. I think conventional wisdom has had it for quite a while, but the first sort of telescope spyglass device was invented by a Dutchman. That's based on patent literature. There were multiple patents filed in very short order. But there's been a really interesting theory proposed in more recent years by the British that there was, in fact, an earlier version of that created by Leonard Digges. And it was kept secret because it was used by the British Navy in order to track the movements of the Spanish Armada. And so not a lot of proof, but it is really clear from a lot of diaries and from his son's documents that he was doing some very interesting things with lenses in order to see for very long distances. And obviously, I think a lot of people here know much better than me the really fascinating history of how telescopes and microscopes and things like that have advanced since then. A little bit of that continuing history is illustrated on the right with some of the real pioneers in sort of the American technological and scientific glass manufacturing capability with some German immigrants, John Bausch and Henry Lohm. They worked very closely with the Carl Zeiss company, sharing patents, even owning, I think that Zeiss owned a good chunk of Bausch and Lomb for quite a while. And as you might imagine, World War I and World War II caused rifts, and so it was a sort of an interesting dance where they came together and split apart, and came together and split apart. But in their early years, they were the premier maker of technical glass in the United States. They did some of the very first work in Navy weapons sighting and were instrumental to basically sort of creating U.S. leadership in that particular field in the post-World War I era. So all of this just to say that glass has had a very rich role for those of us who work in the realm of Department of Defense. So looking back at the past, now let's take a look at some things that we have done fairly recently. So we'll call that today in the sense that a number of these things are actually being used. First on the left, you have the Space Surveillance Telescope. I don't know anyone here who sort of is interested in sort of, Guinness Book of World Records type things, but the SST telescope has a 3.5 meter mirror, and it's quite a feat of engineering. I think that's sort of twice my height and then some, if you want to get a feeling for how big that single concave mirror is. Unfortunately, I would say that while we succeeded in actually building the telescope, this was actually done by MIT Lincoln Lab. We did not succeed in coming up with a cheaper, easier, and repeatable method. So if you were to do another one, it would be just as hard and just as expensive and just as crazy. But we do know that it's possible, and it is actually now in operational use with our partners down in Australia, where it is used to survey the sort of the deep space network, particularly looking for debris and helping to keep the southern hemisphere information sort of flowing there. On the protection side, we have quite a long history, as you might imagine, of developing materials to provide protection for our soldiers. And a lot of that includes work in ballistic glass and transparent armor. I'll talk a little bit more about where we're going with that in the future. And then I think on the even more fascinating side, you have information processing. And so this is where we move into the world of meta lenses, where you have lots and lots and lots of sort of really tiny lenses linked together, where each of them can be sort of programmed to control different properties control light in different ways in order to make it do things that, conventional concave and convex kinds of surfaces just aren't able to do as cleanly. And so in this case, what has been demonstrated is the ability to actually do computation directly. So you're using light coming through the different lenses, and as the change in propagation occurs, essentially it's directly calculating the results of a formula. So it's a type of analog computing, taking advantage of light moving through different kinds of materials. So it's a little sense of, I should also note that most of these things are in some type of use. On the far right, very, very crude, very early days. But if we go to the next slide, then we get to talk a little bit more about where things are going. Try again. There we go. All right, so let's talk a little bit more about those meta lenses. But this is going back to the idea of sensors. And this is actually something that is being commercialized by a little company called MetaLens with a Z at the end, a spin out of Harvard University, and this comes out of that same particular research group, the Capasso group at Harvard. And this comes from a program we have called Extreme. Mostly what you're seeing are pictures of some of the experiments that were being done. On the far right, you've got a real close-up. You can see the 2-micron gauge over there in the right corner of what these meta lenses actually look like. But this is an all-glass meta lens, and this particular thing that we're talking about is 10 centimeters. The size of that is, again, it's not 3.5 meters, it's only 10 centimeters, but from a fabrication perspective, that's actually an enormous breakthrough. And what this lens is able to do is essentially focus white light, so all colors of light, very precisely on a single point. So it eliminates any real issues of chromatic aberration, and it's doing it on a completely flat surface. It's been demonstrated before, but as I said, doing it on something as big as 10 centimeters, which is apparently very scalable, I think is a really exciting breakthrough. What they were able to do was find ways to break up the lithography steps into a bunch of manageable chunks, and then stitch everything back together in a series of sort of sequential exposures that you can actually create larger and larger and larger lenses. So it starts to open up all kinds of fascinating possibilities in both small and larger devices in terms of precision and sort of conformal optics. All right, so let's go back to the idea of protection. And I mentioned transparent armor before. This is one of those things where unfortunately you're always in a race. So we make armor and others make better bullets. And then we have to make better armor. And at some point it starts to get heavier and bulkier and things just get really out of hand. And those of us that are thinking on the defensive side tend to always feel a bit like we're on the losing side of this. But here's some really interesting work we have done in trying to manage the ballistic properties of glass. So the trick, it turns out, is that you want to have the glass, the armor itself, encountering as much of the energy as possible. So if you look at the picture on the left, you might think that what you're seeing in the current ballistic glass looks a lot neater. Basically what's happening is it's sort of fracturing into teeny little pieces, and you get that nice clean sphere. But on the other hand, you might notice that the bullet has gone almost all the way through. On the right-hand side, we've engineered the glass in order to sort of fracture much more broadly and distribute that energy farther and farther away. So in the same time exposure, only a couple of millimeters have gone through. And the end result, if you look at the right-hand side, those are multiple 30 caliber bullets shot at a sort of point-blank type range and completely blocked. And so there's a whole realm of using just the properties of glass, very carefully engineered, in order to completely transform what's possible. Anybody who's ever worked in the armor field, you tend to know that it's actually really complex, and you have layers of ceramics, and you have layers of glass, layers of very interesting fabrics. But it turns out that there is just so much more potential in the glass layers than we have fully explored, that there's a lot of room left to really go. And I think that's one of the things that's particularly exciting about the celebration that we're all having in terms of what is left to be discovered. And I think the answer is quite a bit. Okay, and then let's talk about that information processing. This one hurts my head. And The good news is, for those of you that don't think about this from a scientific perspective, I'm not going to explain it at a level that is any deeper than artists or anyone else might need to understand this, because that's about the sort of the hands-on experience that I've ever had with this. But when we think about neural networks and image recognition right now, so think about all of those deep learning and AI, machine learning algorithms that are out there that can recognize cats on the internet, or dogs or whatever. And I might add, by the way, that you shouldn't get too excited about that just yet. I think it has been shown more than once, for example, that algorithms that are really good at detecting, say, wolves from dogs are not actually doing that. They're actually looking for snow and not snow, because apparently most wolves are photographed in snow. So there's a lot of room there to sort of figure out what's really happening. But in this case, so if you look at the top, that is kind of the projection. Let's say we're looking to do pattern recognition on the number 3. You have an image, somewhere in there is the number 3, and then you're using these deep neural networks in order to try to do the recognition to say, aha, we think there's a 3 somewhere in that image. So it turns out you can actually program the glass to do all the work for you. And so if you look at the bottom, this is sort of the future that I think some people are trying to get their arms around and demonstrate it as really being possible. So the idea is that you can encode the glass itself with information about the shapes that you want to recognize. And as the reflected light sort of propagates through the smart glass, it then is directed to different zones. So in this case, if you happen to see the number 3, the light is programmed to only go to your little pattern bar in the back that says you've detected the number 3. And we're again using that meta lens technology. So each of these little pieces is doing all kinds of different things, but you're ultimately programming the glass to do all the computation, but not just the computation, but now the detection or the recognition for you. There's actually no power needed to do this, it's just the glass. So you can imagine an imaging system that really just lies there and only wakes up when an object of interest comes into the field of view. So it kind of limits, I think we're only limited, in all honesty, by our imaginations in terms of what is truly possible. And it's just a hint at some of the things that might be available in the future. So you can start to think about both the good and the bad of what we're going to have to do coming forward. For example, intelligent glass will potentially start to raise interesting privacy concerns. We do spend a lot of time thinking about ethical, legal, societal implications of the technology that we develop. There are a lot of things related to size, weight, manufacturability, cost, things like that that have yet to be worked out in a lot of the things that we're talking about. There's certainly a lower hanging fruit opportunities in using conventional glass in microelectronics as we start to think about what we need to do in sort of moving beyond Moore's law in the world of semiconductors. So I think what I want to kind of leave everybody with is this idea that we're a long, long way from having written the next big hits that we hope that we and others in the DOD science and technology ecosystem will be coming up with. But I may have given you a little taste, and some of you may have your own ideas on what those are ultimately going to look like. But maybe a decade from now, a successor of mine will be standing up here and showing a whole different set of pictures on the front right of that timeline. So thanks very much for your time and your attention this morning. And congratulations to the International Year of Glass.